PERT analysis is intended for project management when you are not exactly sure how long activities are going to take. PERT analysis essentially relies on gathering several different estimates of potential task time duration. You can see that in this particular scenario. Let's look. The EPIC technical director claims many of the task durations used in the previous analysis, which was oh by the way, CPM analysis, where there's a high degree of certainty, represents worst case estimates. Oh, okay. So wait, what? Last time in the CPM analysis, we were using fixed activity times because we were acting like we knew how many days each one of the tasks would take just exactly. Now we're saying, no, maybe not so. So look what happens. As a result, the director feels the previous analysis represented worst case estimates. As a result, the director feels the project will probably take about 7 days to complete. Now this is an interesting statement, regardless of crashing. The crew all agrees on these detailed duration estimates of the 9 project tasks. You go, huh? What? No, wait. We had a project that had 9 tasks. We had analyzed it in previous scenarios as a CPM problem where we knew how long each one task was going to take. Now we're saying that maybe those were just worst case estimates. That's what this paragraph is saying. Although the director feels like it'll probably still take about 7 days to complete. Now we have this table of data, and it says everybody's agreed on this table of data. Look at the structure of the data. These are the 9 tasks of the project. Oh, okay, that hasn't changed. What we have though is 3 different estimates of time. For each one of the tasks, we basically have 3 different answers to how long it will take. For instance, task A, create technical drawings, it says optimistic time. Frequently abbreviated with a capital O, half a day. Meaning that if everything goes really, really well, it'll take about half a day. Most likely time, abbreviated with a capital M, meaning that most of the time the crew agrees it usually takes about 3/4 of a day. And pessimistic time, frequently abbreviated with a P, meaning that, the worst case scenario is that it will take about a day, and so on and so on and so forth. You see that each one of the tasks, there are these 3 estimates. These 3 estimates are meant to represent an assumption that the true task time, which we're not really exactly sure what it is beta distributed. Oh, by the way, beta distributed? There's a little bit of room down here at the bottom of the page. Yeah, a beta distribution. This is the probability that the task will take a certain amount of time. A beta distribution is kind of lopsided. Usually has a steep side and a long tail. The tall part of it is where the M is, the most likely time. The optimistic time is over here, and then the pessimistic time is basically out here. You say, oh, all right, what am I supposed to do with that? Well, that is the origin of the following formulas. Because notice what the question is with this scenario. Has the critical path changed from the original path of ACFGHI determined in scenario 1C, back when it was a CPM problem? Okay, now that we know all this additional detail, has the critical path changed, or is that sequence of tasks still the critical path? Well, in order to gauge that, we have to now gauge what the expected time is for each one of the tasks, right? Because now we have these 3 different estimates for task length. It might be as little as 1/2 of a day, or it might be as much as 1 day. In order to do the analysis and find out what the critical path is, we still need one number for task length. Now what we're going to do is use this number. Expected time for each task, the optimistic time plus 4 times the most likely time plus the pessimistic time divided by 6. It's basically a weighted average. of the 3. Okay, so in order to confirm or deny that that particular set of tasks that was just quoted to us as the old critical path from our leftover analysis is really actually the critical path right now, what we first have to do is we have to calculate the expected time for each one of the tasks. Now, what are we doing? If just in case you're curious, what's the origin of this formula? It's looking for the one place that cuts this mystical beta distribution in half, essentially. You know, while we're at it too, we might as well fill out another formula for each task. We're going to need this later. Since these tasks vary, we should calculate their variance. That's the pessimistic time divided by, or minus the optimistic time divided by 6 squared. It's basically the range in the estimates divided by 6 and then square the result. And you say, huh? Okay, it's a numerical score for how much the 3 original estimates varied, and we will make greater use of it later, but as long as we're crunching numbers, we might as well just go ahead and calculate it now. Oh, right, so, you know, one thing that might be handy, or a lot of times working one of these problems, you know, we could like set up another column here and let that be expected time, you know, and then work along these rows, filling out the formulas, and maybe that be variance. But you notice how I'm running out of room here on this particular note sheet? That's why you could still do this, because you can probably write smaller and neater than me. But if you have the note frame, there is some room to work here on the second page. I'm going to draw some lines just so that I keep all of my numbers straight. Let's see, there's 9 tasks, so what will work is if I draw 5 lines. There's 1, there's 2, 3, 4, and 5. Now, why did I do that? Because this is where the name of the test, let's see, A, B, C, D, E, F, G, H, and I. Goes up to I, right? Yeah. Okay. Oh, great. And the formulas are already provided again on the next page. I just need to fill them out for each one of the tasks. For instance, there's the timings for task A. So its expected time would be, let's see, the optimistic time is 0.5 plus 4 times the most likely time is 0.75 plus the pessimistic time is 1. I do all that in the numerator. I divide by 6 because it's essentially a weighted average. And what did I get? I got 0.75 back again. Okay, 0.75. That's the expected time for A. For B, for instance, same formula. Just say 1 plus 4 times, let's see, for B, the most likely time was 2 days, plus the pessimistic time is 3 days. That's all the numerator. Divide by 6. I get 2. Okay. 2 days. For C, same thing. Pick these numbers up. Put them in the formula. 0.5 plus 4 times 1.5 plus 4 divided by 6, I got 1.75. Now, that's me figuring the expected time. I had said it would be handy to figure out the variance also in each case. Now, in the case of A, the pessimistic time is 1 day. The optimistic time is a half a day. There's the numerator. Divide that by 6. Square the whole thing. I get 0.0069. Great. That's the variance in task A, 0.0069. Same thing for B, same formula anyway. I say 3, remember actually it's over here, the pessimistic time, minus 1, the optimistic time. Okay, that's 2 divided by 6, square the whole thing. I get 0.1111, repeating. Yeah, okay. For C, the pessimistic time, right, is 4. 4 minus 0.5 means you have 3.5 in the numerator divided by 6 squared. Okay, 0.3403. Now, for D, if you fill out the expected time formula, let's see, that would be 1 plus 4 times 1.5 plus 2 divided by 6. This is for D. I get that the expected time is 1.5. You can check me on that. And then if you say for D, the 2 minus 1 divided by 6 squared, okay, well that's 1 divided by 6 squared. I get a variance of 0.0278. For E, I get an expected time of 1, just using that same formula. I get a variance of 0.0278. Again, it has the same variance as D because it's 1 over 6 squared. Then over here for F, okay, 1 plus 4 times 1.5 plus 2 divided by 6. I get 1.5 days is the expected time. And then for the variance, I get another 1 divided by 6 squared, or on the calculator, 0.278. Let's see, for G, I get 0.5 times 4 times 0.75 plus 1 divided by 6. 0.75 is the expected time. Okay, great. The variance, I get another 0.0069. For H, 0.5 plus 4 times 1 plus 1.5 divided by 6 is an expected time of 1 day. A variance, here's another 1 divided by 6 squared, 0.0278. And then I, also an expected time of 1 day, also a variance of 0.278, because you'll notice it has the same original data here as H, so it's going to have the same summary statistics. Oh, all right. Now, what did we do all that scratch work for? This is the first phase of a PERT analysis. You've gathered these 3 time estimates, and you crunch the numbers to create for each task an expected time. This is what you're going to plan on, and a variance. What's the variance for? Hang on to that thought. We really aren't going to use that information until later in the analysis. It was just handy to do it right now. Oh, okay. Now, back to, wait a minute. What were we trying to do? Back to the question. The question, when we started on the formula, was has the critical path changed? Okay, now this, okay, we want to confirm that that is still the critical path, or report that it's not. That means we have to find the critical path. If you have the note frame, this is right here the original network diagram for the Epic Scenery Studio project that we're working on. Notice that, you see how it looks familiar because I was looking at the CPM scenario too, you know, the one that came before this one. But okay, if it looks familiar, notice that the task durations now are different from the ones we were using for the earlier scenario. As a matter of fact, wait a minute, what are those numbers? A 0.75, B 2, E 1, they're right here. These numbers, copy them. If you were doing this yourself, you know, you'd have to draw the network. You would take these numbers that I wrote in green ink, the expected times, and that's what you would put on the network as how long you think each one of these tasks is going to take. Oh, all right. Having done that, why have you done that? Because you've set yourself up to find the early start, early finish times. Okay, early start, early finish times begin at the starting node. Well, that's right here. Yes, everything attached to the starting node, which is just A and B, no problem, automatically has an early start time of 0 because you could start on it right now. Now do the arithmetic. 0 plus 0.75 means the earliest we expect task A to end is in 0.75 days. In the case of B, 0 plus 2, the earliest we expect to be done with B is in 2 days. Now we work our way through the project. Okay, well, E and C, I'm just looking at the network, cannot start until A finishes. That's what these arrows mean. A, we expect will finish at the earliest in 0.75 days. Pass that number forward. That is telling us the earliest we might possibly start on those two tasks that are waiting. Okay, 0.75 plus 1 is 1.75. That means the earliest we might finish with E is in 1.75 days. 0.75 plus 1.75 is 2.5. The earliest we might finish with task C we now expect is in 2.5 days. Let's see, D can't start until B finishes. B will finish at the earliest in 2 days, we expect, so that, pass the number forward, becomes the earliest we might start D. D, 2 plus 1.5, might be finished at the earliest we expect in 3.5 days. Okay, now F. F is just waiting for C to finish. Oh, now we know that C could finish at the earliest in 2.5 days, so pass that number forward. F might start at the earliest in 2.5 days. 2.5 plus 1.5 is 4. Task F might finish at the earliest in 4 days from now, and we're done with this when we have filled in all of them. Let's see this one, G. Oh, G is one of the tasks that we might want to take this a little slower. Why? Notice that G has more than one predecessor. There's more than one arrow pointing at it. That means that G can't start until both D and F finish. Okay, D could finish at the earliest in 3.5 days. F could finish at the earliest in 4 days. It's waiting on both of them. Therefore, we take the larger, the early start time rule. The early start time of an activity is equal to the largest of the early finish times of activities that immediately precede it, that point at it. Okay, anyway, it could start at the earliest in 4 days. 4 plus 0.75 is 4.75. That's when it could finish up at the earliest. H is waiting on G to finish. Okay, we'll just pass the number over then. It could start at the earliest in 4.75. 4.75 plus 1 is 5.75. It might finish at the earliest in 5.75 days. And then finally, I, up here, oh wait a minute, be careful, has more than one task pointing at it. I cannot start until H and E finish. That's what the network is saying. E could finish at the earliest in 1 3/4 days, 1.75, but H won't finish until the earliest in 5.75 days. Pick the larger. Well, I's waiting on both of them, so I's just going to have to wait to 5.75 at the earliest. 5.75 plus 1 is 6.75. The early finish time for task I is in 6.75 days. That is a critical turning point in finding the critical path because we now know something. The expected completion time of project 6.75 days. Why? Because the very earliest we expect to finish what's essentially last task in the project, the only thing that is attached to the finish node, is 6.75 days. When it's finished, the project's finished. Oh, therefore, what was this? We were building a stage at the San Diego Convention Center was the original context of this. If we start right now, we expect that the earliest we could be finished is in 6.75 days. Oh, all right. Now, wait, the question was about the critical path. All right, where's the critical path? To find the critical path, now we have to find the late start, late finish times. We have to begin at the finish node and work our way back to the start, and we begin at the finish node with that fact that I'm obsessing on at this moment. We could get this done in 6.75 days, we expect. Therefore, we make that the deadline. Anything attached to the finish, which is just this task I, has to finish at the latest in 6.75 days. We insist. Okay, 6.75 minus 1 day's worth of work means that I has to start at the latest in 5.75 days in order for everything to stay on track. Okay, it has to start at the latest in 5.75 days, and it can't start until, trace the arrows back, E finishes and H finishes. Therefore, take that number and make it their deadline. H has to finish in 5.75 days at the latest. E has to finish in 5.75 days at the latest. Now 5.75 minus 1 for H is 4.75. That's the latest it can start without creating problems. In the case of E, 5.75 minus 1 again. Oh yeah, okay, late start time 4.75 over here as well. Now we keep working our way back through the network. Okay, for instance, down here we've just now discovered that H has to start at the latest in 4.75 days. It can't start, follow the arrow back, until G finishes. That's its new deadline. It has to finish at the latest in 4.75 days. 4.75 minus 0.75 is 4. Its late start time is 4. G cannot start until, what does the arrows mean? F and D finish. It has to start at the latest in 4 days. That becomes their deadline. They have to finish at the latest, each one of them in 4 days. 4 minus 1.5 is 2.5. F has to start at the latest in 2.5 days. Over here, 4 minus 1.5 is 2.5. D has to start at the latest 2.5 days from now. And just keep filling these out. Okay, look at F. We now know that F has to start at the latest in 2.5 days. It can't start until C finishes. Pass that number back. C has to finish at the latest in 2.5 days. 2.5 minus 1.75 is 0.75. That means that C has to start at the latest in 0.75 days. See down here, D, we now know, has to start at the latest in 2.5 days. It can't start, I'm just following the arrow back, until B finishes. Therefore, that's B's new deadline. At the latest, it has to finish in 2.5 days in order to not delay D. 2.5 minus 2 is 0.5. B, its late start time is 0.5 days. We could wait as late as a half a day before we start it. Now we only have one other one to fill out here. And this one we might take a little slower. Okay, what is the late finish time for A? Well, E is waiting for A to finish, and C is waiting for A to finish. A has more than one follower. Okay, E has to start at the latest in 4.75 days. C has to start at the latest in 0.75 days. We don't want to delay either of them. They are both waiting on A. That means that we should appropriately pick the smaller number when we have a choice, because we don't want to delay anybody. Okay, that means A has to finish in 0.75 days at the latest, so it doesn't delay the start of C. Now 0.75 minus 0.75 is 0. The late start time for A is 0, and I am really glad to see that. Okay? Because especially working backwards through the network, that takes a little bit of practice. That can be a little bit tricky. By the time you work your way all the way back to the start, at least one of the tasks attached to the starting node needs to zero out. You need to naturally conclude when you do the subtraction that the late start time is 0. If that's not true, then it's a hint that there's a mistake. There's a bug somewhere with your math, but we did. A zeroed out. Okay, now we expect this project is going to take 6.75 days, which is an interesting consistency with, where's the start of this? Something that the director said that it would probably take about 7 days to complete. We're at 6.5. Okay, but the question is, this was from the CPM analysis, the old critical path. Is that still the critical path? We think, oh, wait, the critical path is the set of all activities with 0 slack. So now I can set up a table and I can calculate the slack in each one of these activities and identify which ones have 0 slack. Yes, we could do that. We don't need to, because the set of all activities with 0 slack will be the set of activities that when you're looking at our work, the two timings match. So if you subtracted one from the other, you would get 0. See how they match there? And then for C, they match. And then where else do they match? They match for F. And then they match for G. And then they match for H. And then they match for I. And I checked that this is indeed a path. There's the start. You can get to A. Yes, then you could get to C. Then you could get to F, to G, to H, to I. And that is attached to the finish. Okay, critical path. A, C, F, G, H, I. Wait a minute. A, C, F, G, H, I. Answer to their query, no, the critical path did not change from the earlier analysis.